Hey guys, this is the makeup lecture for section 2.9 from the Chimera text on our inverse trig derivative rules. Now if you're sitting through this section, we've hopefully very recently wrapped up the section on implicit differentiation, which is a technique that I mentioned to you guys that we would need to be able to tackle finishing some of our rules on dealing with things like inverse trig functions and the natural log function, which we'll touch on later. So for us to tackle these, we're going to need to do a brief recap on inverse functions and how those work. So let's go ahead and get started. Alright, the first thing I'm going to have you guys recall, okay, hopefully you've seen this before, it's basically what an inverse function is and what it does in the first place, right? We'll say that f inverse of x, this guy is an inverse function for f of x if the following things happen. If I compose f with the inverse function, what's going to happen here is that these are basically functions that undo each other. So my f and my f inverse should cancel out, and I'll basically get back whatever it is that I plugged in to start with. And this is not only going to happen in that direction, this will also happen if I compose them in the opposite order. So if I take f inverse of f of x, I'll get a similar cancellation, right? So these are totally two functions that undo the action of the other, and you just get a cancellation, you get back what you started with. Now, for some examples of this, you guys have probably seen both of these before. If I look at a function like the exponential function, and I pair this with, well, the inverse of this guy is going to be the natural log function. Okay, if you take log of e to the x, it cancels and you get x. If you take e to the natural log of x, it cancels and you get x. Both those guys undo each other. Another example that I am certain you guys have seen before, if you start out with x squared, what undoes this function? Well, the obvious, right? You look at the square root function, which is a half power, or, you know, we'll write this as root x. Now there is a small catch here. Whenever you're looking at inverse functions, you do have to be a little bit careful about the domain. So it will specify this is for positive values of x only, that these guys are inverse functions. Reason that I say that is that if you start with a negative number, negative x value, and then you square it, you're going to get a positive that when you plug it back in here, you're just going to get another positive number back. So if you start with a negative, it doesn't quite cancel to exactly what you started with when you compose these things. But for positive x, everything comes out positive, so we're fine. So as a comment, you know, those are some general inverse functions. What about the ones that we're looking at today? The examples that we're focusing on today are basically going to be all of the arc trig functions, right? All of the arc trig functions. These guys are inverses on appropriate domains to the corresponding trig functions. So in other words, if I'm pairing something like f of x is sine x with its inverse, well, in this case, your inverse function is going to be arc sine of x. Now, a comment on notation. For this particular trig function, arc sine and all the other ones, arc cosine, arc cotangent, arc secant, arc, etc., you know, all of them. All of my arc trig functions can also be written in inverse notation. So if you see things like sine inverse of x versus arc sine of x, these are the exact same thing. They're just different notations for using the same function. One of them requires you to write a couple fewer characters, which is usually why we like using it. So we get to make that comment, and, you know, similar for my other trig functions. Now, the reason that I'm making a big point in the notation here is I will highlight this point. This is super important to recognize. My -1 in this case, this guy means inverse, right? This absolutely positively means inverse, and not, and write this in big, bold, capital letters, it does not mean 1 over your trig function, right? Now, the reason for this, even though it is a little bit ambiguous, I've mentioned before, whenever we see this notation, it's expressed as a power, like sine squared, sine cubed. This is the one exception to that case. We never, 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 never want to interpret this as a power. Reason being, if I wanted 1, didn't mean to draw that line, if I wanted 1 divided by a particular trig function, well, all of the trig functions that we have named reciprocals. For example, if I wanted 1 over sine, I wouldn't say 1 over sine, I would say cosecant instead. If I wanted 1 over tangent, I would say cotangent instead. So we don't really have a reason to ever write a trig function raised to the -1, because, you know, we're usually not going to try to write that instead of just using the reciprocal in the first case. So, just side note, whenever we see this, interpret it as the arc sine, don't interpret it as 1 over sine. Okay? At any rate, now that I know which trig functions or trig inverse functions I want to worry about deriving, how do I derive these things in the first place? Here's going to be our setup. If I'm looking for the derivative of a particular inverse trig function, we're going to go ahead and set up y equals whatever the heck that was. So if we wanted the derivative of arc sine, we'll set up y equals arc sine. If you wanted the derivative of arc tangent, you set up y equals arc tangent, etc. And once you have that, we're going to compose both sides with the appropriate inverse. Okay, so if you started out with a sine inverse over here, compose both sides with sine. So take sine of both sides. If you started out with a cosecant inverse over here, take cosecant of both sides. And then after that, we're going to do implicit differentiation on whatever it was we got. Now, as a recap, this was our last section, hopefully. We're going to derive both sides, separate your dy dx terms from your non-dy dx terms, and then solve for dy dx. You'll notice that if y started out as the trig function or trig inverse function that we want to derive, dy dx should give us its derivative. So let's actually try this for an example. I want you to find dy dx if y is the sine inverse function or the arc sine function. Okay, so let's go ahead and do what they said. We've already accomplished the first step, set y equal to the function that we want to derive. My next step from here is to compose both sides with the appropriate inverse. Now, the thing that pairs up with sine inverse is the sine function, so I am going to hit both sides of this with that sine function. Right? So I have sine of sine inverse of x on the right-hand side of the equation. The nice thing about this, since these are inverses, we've gone over the fact that those cancel, and you should get back whatever it was that started out on the inside to begin with. So I now have that sine of y is x. The reason that that composition gives us a nice problem setup is before we have had no clue what the inverse sine function's derivative looks like. We don't have a rule for that yet, but we do have a rule for the sine function. And since we have implicit differentiation now, we can tackle the fact that the y is on the inside. If I implicitly differentiate this, the first step is to take the derivative of both sides with respect to the variable x. Now, if I do that, your derivative of the sine function is cosine. Since this was written in terms of y, though, we're going to tack on a dy dx. On the other hand, on this right-hand side, the derivative of x is just 1. Nothing special happens there because we're deriving both sides with respect to x, and that's what we normally did. Derive x with respect to x, you get 1. We don't have to do any work to separate this. It already is automatically separated. So the last step in implicit differentiation here is just to solve for dy dx, which we accomplish by dividing both sides by cosine of y here. Now, this is kind of a crappy derivative rule as it currently stands. Reason being, we started out with a function of x to derive, and now we have this formula that spits out something in terms of y. That's almost certainly not what your textbook is going to give you as a direct derivative for the sine inverse function. Plus, there was kind of that point I mentioned earlier about usually not wanting to write these trig functions as reciprocals. So there's got to be something that we can do to fix this and hopefully make it spit out something better in terms of an x variable. Now, to do this, here's our trick. We are going to use the Pythagorean trig identity, which is going to state that my sine squared of y plus my cosine squared of y is going to give me 1. Now, if you manipulate this guy by solving for the cosine function, and if you're careful about which chunk of the domain that you're on here, if you solve for cosine, this means subtracting sine squared from both sides. So I'll get 1 minus sine squared of y, and then to get rid of the root, you're going to root both sides. Okay? So what I'll go ahead and do here is make note that this cosine of y, this is the same exact function as this guy, right? So what this will tell me, if I wanted to rewrite my dy dx, I'll get that, so we can see it here, dy dx is really 1 over this square root. So sine squared of y. Which, another way that you can write this, which actually may be a little bit more useful to us here, is I can also think of this as sine of y, that whole quantity squared. It's the same thing. Now, this is still written in terms of y, which is problematic, but there's an easy fix for that. If I take a look at what we defined y as in the first place, up top here, we said that y was the sine inverse function. So I'm going to take that information and substitute it back into our current state of the problem here. I've got 1 over the square root of 1 minus, instead of y, I said we would substitute in the sine inverse function because that's what it said y was up top. Okay, and that whole thing is being squared. Now, this is also not the form that you're probably going to see it in your textbook, reason being, we have another nice property of inverses where those guys cancel, so what this boils down to in the end is 1 over root 1 minus x squared. So this guy is going to be our derivative of that function y. So just to recap, here's the rule that we're getting back. My derivative of the sine inverse function, or the arcsine function, this is 1 over root 1 minus x squared. Okay? Now comment, I don't want you guys to do this every time that you see an inverse trig function. There's a lot faster of a way to do it. We have formulas for each of these things. Now, we just derived the one for sine inverse. If you do a similar trick for all of the other inverse trig functions, you'll get each of these formulas. So I'm just going to give these to you guys right now and assume that you can take these for granted at this point. Okay, we already derived it once. You can see that I didn't pull the formula out of the butt and out of my butt, and it does come from somewhere. We'll go ahead and assume that the rest of these can be derived in a similar manner. Now, we do get a couple nice patterns out of this, kind of like we did for the regular trig derivative rules. Namely, all of my c functions, again, are still negative when I look at their derivatives. And all of my co-functions pair up very, very nicely in that if I'm looking at a pairing like sine and cosine, or tangent and cotangent, etc., if I look at those pairings, they use the same exact formula up to that sine difference. Okay, so my sine, tangent, and secant inverse trig rules, once you memorize these guys, if you remember the pairing and the fact that it should be negative, you get the other rules for free. So now that I'm saying that we can take these for granted, let's see if we can crank them out in a couple examples. For this first one, we're taking the derivative of 7x cubed times the arc sine of x. Do not forget, arc sine and sine inverse are the exact same thing, so this is the same question as if I'm asking you guys to derive 7x cubed sine inverse of x. So we're going to need product rule for this because technically there is a product here. If I view this as f and g, what I'm really going to want is f prime, which is 21x squared. I want this times g, which is just copying this thing over. And I want to add this to f, which is 7x cubed, times g prime. Right? And if I actually recall from that last example, we just did this one. This is 1 over root 1 minus x squared. Okay? Not too much simplification we can do for this particular question. Maybe if you wanted to actually multiply this out so that you have 7x cubed over that root. So we'll largely just leave that one be. Let's try another one of these guys. Here I want the derivative of cotangent inverse of a polynomial. Now we can go ahead and note this is a composition of two functions, so I'm going to need chain rule here. Right? Do note that your outer function is this cotangent inverse of something. So when I go to derive this thing, I'm going to note that my derivative of my outside, per the table that I just put up, was minus 1 over 1 plus something squared. Now, if I fill in my inside function, my x squared plus 5x minus 10 is going to go here. But I'm not done yet because we said we were doing chain rule. We also need to tack on the derivative of the inside, which is going to be 2x plus 5. Okay? Again, if you want to, you can write this guy up in the numerator because that's how multiplying a function by a non-fraction or a fraction by a non-fraction quantity is going to work. Okay, we'll just multiply this right across the top. Let's see if we can try another one of these chain rule questions. Let's try the derivative of secant inverse of e to the x. Now again, we've got a inverse trig function as my outer function. This is going to be secant inverse of something. Sorry about my pen flubbing up here. So if I take the derivative of this guy, by chain rule I need the derivative of my outer function, which will be minus 1 over absolute value of something times square root something squared minus 1. Okay? So this is actually kind of similar to our secant and cosecant original trig function derivative rules, in that once you take the derivative of this function for chain rule, you're going to get two spots in which you're going to have to play fill in the blanks. Now, my original inside function was e to the x, so I will copy that over in both of these locations. This is not where we're done, though, because we were doing chain rule, right? We need to tack on the derivative of the inside function, which is e to the x. Now this guy, I will make a comment. This one does simplify actually kind of nicely. My side comment that'll let us do this is the following note. U of the x, this guy is always, always, always positive. You know, if we graph this, here's 1. The exponential function has this horizontal asymptote of y equals 0, and it never actually does cross that line. We always get positive values. So if I'm using that bit of information to simplify here, okay, we had minus e to the x up top if we multiply through. If I'm using this bit of information to simplify here, we're taking the absolute value of a positive, so I don't really need the absolute value signs. I can go ahead and just get rid of them. On the inside here, we'll make a comment. If you have a power raised to a power, you multiply to simplify. So if I want to clean this up, I can perform a cancellation to give myself a slightly simpler version of this derivative, okay, if I actually needed it to do something. So in this particular case, my derivative of that function comes out to this. We'll do one more of these. I've got sine inverse of the cosine function. Again, just for the record, we have worked with this derivative function. This is the one we derived. If my outer function is sine inverse of something, this means that my derivative per chain rule is going to be 1 over root 1 minus something squared. This was the one that we derived. Now, we have to copy over the inside function, and we also have to multiply by the derivative of the inside function. So this is going to give me a minus sine of x here. So if I think about how this is going to clean up, let's take a look at what's going on in the denominator, right? Remember, we had that trig identity that we were using earlier that said that my sine squared of x plus my cosine squared of x is equal to what? 1. So if I think about subtracting cosine squared from both sides, what this is going to tell me is that this really simplifies down on the bottom to the square root of sine squared of x. Okay, and actually this expression here can simplify a little bit further because we're rooting a square. We do have to be a little bit careful about how this simplifies though. Remember in the very first slide of these notes or page of these notes, I mentioned that these are only inverses if you're getting a positive number to start with. Basically, if you plug in a positive, this is going to eventually spit out a positive, and if you plug in a negative, it'll eventually do the same thing. Really, what the square root of a square is going to simplify to is actually the absolute value function, right? We know that if we started with a positive value for sine of x, it'll come out positive. If we started with a negative value, it'll also come out positive. So we've really got this guy over its absolute value, and I'll go ahead and note, depending on what sine of x started out as, if my sine of x is positive, we'll note this is going to equal, well, -1, because those would cancel otherwise. And on the other hand, if my sine of x is negative, well, let's think about this. We have a minus sign multiplied by the sine of x. If that thing started out as negative, my negatives cancel each other out. So this is going to come out to +1. And this is kind of a weird derivative, but I actually have the picture of this original function, sine inverse of cosine of x, down here. we scroll down a little bit, we kind of get this weird Charlie Brown looking function. So this indeed is a function that, you know, depending on whether sign is positive or negative, we alternate between different slopes here. On some intervals the slope is positive 1, and on some intervals the slope is negative 1. So it's actually kind of a neat little function here. We'll try one last example to round this out. I'll actually have you guys do an application. You can find an equation for the tangent line to the function arctangent of 2x at x equals a half. So first off, recall you are going to need the point, and you are going to need a slope to get this tangent line back. Now for my point, go ahead and plug this value into the function. I'll take f of 1/2 here. This is going to be my tangent inverse of 2 times 1/2, which is my tangent inverse of 1. Be really careful here. The range of my tangent inverse function is limited. If you stick this guy into your calculator, or if you are familiar with your unit circle, you'll note that this is the angle pi over 4 here, which hopefully makes sense. If we're at pi over 4, sine and cosine are the same thing, so sine divided by cosine will be 1. If the angle that we take to get a tangent of 1 is pi over 4, you know, the inverse function should send us backwards. So it should send us, instead of from pi over 4 to 1, it'll send us from 1 to pi over 4. So this is going to give me a point over here. I'll go ahead and make this note. My point is going to be a half pi over 4. Okay, so we have that bit of information there. Now for my slope, we basically want to take my f prime and then plug in a half. Okay, we'll go ahead and do this here. My f prime of x, if you're starting out with the tangent inverse function, your derivative of tangent inverse of something is 1 over 1 plus, if you refer to the table, something squared. I have to fill in my blank with my original inside function, and I also have to tack on the derivative of my inside function. So if I clean that up so that I can actually use it here, I did say whenever I had you guys take a derivative, I would expect you to simplify if you were going to use it for something. This will be 2 over 1 plus 4x squared. So if I'm interested in my slope, we said we had to plug in 1/2. Well, this will be 2 over 1 plus 4 times, well, a half squared is going to be a 4th. So I can kind of give myself a little bit more room here. Order of operations will have me do the multiplication first. This will be 1 plus 1. That should be 2 over 2, which obviously simplifies to 1. So again, this is supposed to be my slope for my tangent line. Now we just said that the point is this guy, and my slope is 1. So again, my point is a half pi over 4, and my slope is 1. If I want to combine this into a tangent line, well, we know that y is equal to mx plus b. I can go ahead and substitute some stuff in here, right? Pi over 4 is 1 times x, which is a half, plus b. It's going to look a little bit messy, but simplifies to a half. Pi over 4 minus a half is going to be my b. Looks messy, but it's still constant, it works. So my tangent line that I was looking for in the first place is going to be y equals m, which is 1, times x. I won't write the 1 in front of the x, you don't need to. y equals mx plus b, so plus this guy. Yeah, this awkward y-intercept on the end, but it still works for a tangent line. So this basically wraps up the lesson, but to make sure that you guys actually watch the video, I will give you guys a quiz for the road. At some point, at your earliest convenience, I would appreciate if you guys turned into me the following. Evaluate the following two derivatives. Derivative of quantity of x squared plus 1, tangent inverse of x. If this is not clear to you guys, I am expecting that you interpret this as take the derivative of that whole product. And also please take the derivative of cosecant inverse of x cubed. If you have any questions, please feel free to let me know.